Okay, welcome back, everybody. This afternoon, we have one talk and one more open problem session. It's a pleasure to introduce Gady Kozma, who will speak about linearly reinforced random walk.
Okay, everyone can hear me? Okay, so linearly reinforced. Let me start by defining this model. And the definition is very simple. You have a graph. And you have some positive parameter A, which is the initial weights. And then you perform a random walk with some interaction which goes like this. Here's the first step. You stand at some vertex. You look at your neighbors. Since you just started, all the weights are A. Because, right, I didn't call them initial weights for nothing. In the first step, all weights are A. You see, okay, A. You normalize that to probabilities, so quarter, 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 quarter. Then you choose according to this probability your first step. So say you went first step in this direction. You get to a new vertex. The edge that you traversed, you increase the weight by 1. So now this edge becomes A plus 1. Now we are in a new vertex. You see some edges. Edges that you haven't traversed are A, exactly like in the beginning. But you see one edge which has probability A plus 1. So you see A plus 1, A. You normalize them to be probabilities. So you get 3 times A divided by, I guess, 1 plus 4A. And once you get 1 plus A divided by 1 plus 4A. So these are probabilities. You choose your next step according to these probabilities. You walk and you increase the weight by 1. So for example, if your second step would be in this direction, then you increase the weight to A plus 2. And then you would have your A plus 2. And you continue this way. Is the model clear? Okay, so I guess the first thing people are asking themselves, is there any relation to Anderson model? Or is this just some random guy talking about the random probability question? So the answer is A, that the relation is vague. Don't expect any like one-to-one reformulation. And also that it will take me at least 20 minutes to get to it, because we need to we need some setup. Okay, so don't keep your whatever on as some people say. Okay, but there is a connection. Eventually we will get
this.
it.
Is purely classical.
Yes.
Just this
But the probabilities change, which changes the picture, which makes it highly non-trivial a priori, and everything that's known on it, somehow this volume changes too much. Everything that's known on it is using the specific properties, algebraic properties, and I will get to that immediately. Okay, so let's do a very simple example to get to show you that it's not a random walk. So let's take a graph with 3 vertices. And initial weights A equal to 2. And suppose you start in the beginning. Okay, let's see what happens. Okay, you start with weights 2, 2. You walk in one of them, say this, you get 3. Then you have to go back. You get 4. Now you get probabilities 1 and 2. You choose according to them. And you add 2 to whatever edge you choose. So what did we get? We got a Polya urn. Just a classical Polya urn. Right, what is a Polya urn? You have an urn with K white balls and L black balls. You pick one of them, and then you put back 2 balls of the same color. It's exactly the same model. Now Polya urns, of course, what happens is that it converges to a non-trivial limit. right? If you look at the polyhedron after you start with like two balls, black and white, then it's a classical fact, I guess, it goes back to Poyer, that after n step, the number of white balls, the proportion of the white ball converges to a variable which actually is just uniform. But non-trivial, that's the whole point. It doesn't converge to half n. Okay, so you see that you have here that somehow the self-interaction causes, it's certainly not the case that it will eventually go approximately half of the time on each edge, far from that. Okay, so that's a first indication this model has some interesting properties. Let's try to see what happens in a slightly more complicated graph. Okay, so in order to proceed, we have to understand a very interesting property of this model, which is called partial exchangeability. What is partial exchangeability? When do we say about a process that is partially exchangeable? We say that when the probability to traverse a given path depends only on how many times you traversed each edge. Let's see an example. Okay? So suppose our graph G is just a triangle and A is 1. And let me let's see what happens with these two paths, okay? So first path is going like this, and the second path is going like this. So there are different paths, but of course, they traverse each edge equal number of times. You notice that it's not directed. So here you traverse this edge left and right, and here you traverse it in the same direction, but I don't care. I'm saying that these two paths should have exactly the same probability. Let's see why. Okay, let's do this example. So you start here. So at first, your weights are 1, so you do this step with probability half. Now your weights are 2 and 1. So you go, and you go in a favorable direction, so your probability is 2/3. Now your weights are already 3 and 1, but you go in the non-favorable direction, so the probability is 1/4. And last thing again, in a non-favorable direction, probability is 1/3. These are the probability of all the steps, and the probability to do this path is the product. Okay, let's do it here. So it's half, 1/3, 1/3. And now when you got here the second time, you got 2 and 2. So let me write it 2/4. So you see that the numbers are different, but the product is the same, because the denominators and denominators are a permutation of one another. Here the denominators are 2, 3, 3, 4, and here the denominators are 2, 3, 3, 4. The denominators are 1, 2, 1, 1. The denominators are 1, 2, 1, 1. They are not matched, but you get the same product. Okay, and that's the proof. Basically, I given you the proof. So that's partial exchangeability. Again, the probability to traverse a path depends on how many times you went through every edge, but not on the order in which you did it. Questions about partial exchangeability? The conclusions are even more amazing. Okay, so what can we conclude from this partial exchangeability? So this whole thing relates to De Fineti's theorem. So let me remind you what is De Fineti theorem. I don't know how exactly to use that effectively. Okay, so De Fineti. 59. Suppose xi are some random variables, and suppose that the joint distribution, okay, xi I from 1 to infinity. It's important in De Fineti theorem that you have infinitely many variables. And suppose the joint distribution is invariant to permutations. So you have some random variables, nobody telling you a priori how they are related, but they are telling you that, for example, if you replace x1 and x2, you get the same distribution. You replace all of x1 up to x100 with all of x101 up to x200, you get the same distribution. Okay, so certainly IAD satisfies that, but the following also satisfies that. First of all, you take a big coin, you throw it, you decide, you see if it comes tails or heads. If it comes tails, you take IAD 1/3. If it comes heads, you take IAD 2/3. Okay? And you look at this distribution that you get. And of course, this is also invariant to permutations. And definitive theorem says that this is the only case. And it's formulated as a mixture of IAD. So again, what is a mixture of IAD? You first of all make one choice, random choice of a distribution. And then once you have this distribution, you take things IAD, and then you integrate over your initial random choice. Okay? Is it clear what's a mixture of IAD? Should I? Okay. Okay. So let me just not get the years incorrectly. So this is 80, not 87. Sorry. So Diaconis and Freeman. Freeman or Friedman?
Friedman.
Friedman, okay. 80. If you are partially exchangeable, and recurrent also, but let's not spend too much time. You need this condition also. Then you are a mixture of random walks. Okay, so partial exchangeability, which is exactly this property, implies that, again, what do? You throw a big coin, you get some environment, which in the case that you are partially exchangeable in a symmetric way is a reversible Markov environment, and then you do a random walk on that. What people today usually call RWRE. But this mixture somehow gives you a nice, so it gives you a nice comparison between these theorems. And in fact, and all of this is completely soft. Definitive theorem is basically an application of Krein-Milman. Okay, you identify the extremal points of some convex set in a Banach space and use Krein-Milman, and the Diaconis-Friedman basically uses definity on the return time. So everything is soft, no calculation involved. But you get a very interesting result, a result which is, I think, I'm not sure even it's even so trivial for the Polya Ern, that you can construct a process which is identical to Polya's Ern as follows. First, you choose a number uniformly between 0 and 1, and then you just take IAD according to this number. Okay, it's certainly classical that it's the same, but you get here you get here from the behavior, but you get a completely soft argument that gives you that there is some distribution, and then you have to calculate it. It depends on the initial conditions. Yes?
Are the random walks characterized by weights on edges?
Yes.
In the RW or
Yes. It's a reversible. You also have a non-reversible version, which Sabo used for his Dirichlet random walk, but I'm not going to go there. It's related, but there are lots of related things. Okay. Okay, so we have what we got that on any graph that we take, so at least finite, let's restrict to finite for a second, there is some measure, some random environment such that linearly reinforced is equivalent to random walk with this random environment, but we learned nothing about what this random environment looks like. So, and to learn that, that's a much trickier thing. The formula is extremely complicated. I'm not going to write it. But I'll give you a slight hint of how the formula comes around. So how does the formula comes around? Okay, so we know that you have your graph. You know that if you write some numbers on the edges, then all paths that traverse this graph and traverse this edge 10 times, this edge 20 times, okay, that's a bit difficult because, no, okay, no, it's not difficult here. And so on, they all have the same probability. So let's try to understand how to, so what we need is not to estimate the probability, but how many paths exist that traverse, the calculation of the formula requires us to calculate at some point how many paths traverse traverse the first edge 10 times, the second edge 20 times, and so on. So in order to make life easier, I'm just giving you an indication of how it works. I'm not going to give a full proof, and the formula is terrible. Let's do it directed. Okay, so let's suppose somebody tells you that you traversed in this direction 1 time, and in this direction 9 times, in this direction 9 times, and now they have to satisfy some kind of regularity, right? You have to go, there has to be some, right, the number of times you enter and exit every vertex must be the same, except at the beginning and the end. And you want to calculate how many paths exist. How do you do that? Well, let's look at the tree of last exit. Right? If you have some path, it reaches some vertex, I don't know, 100 times, and eventually gets out through one of the edges that leaves the vertex. So that gives you, and you remember just these last exit edges. Now, of course, that must be a tree. You cannot have a cycle of last exit edges, right? Because if you had a cycle of last exit edges, you eventually get to an edge which you are supposed to have already exited for the last time. So that cannot happen. So this means that these last exit edges create a tree directed toward you, directed toward your end. Okay, and here is the point. Given a tree of the last edges, the choices of where to go are completely arbitrary. So that's a combinatorial claim. Okay? If you know that you had to exit this edge 5 times in that direction, 6 times in that direction, and the last time in this direction, then the non-last one, the remaining 10 ones, you can go any way you want and you will get a legal path. Because you can never get stuck. As long as you always have some way to get out until you get to the last point, and then you went out through the last point, and you cannot return to the point because of the fact that you know once you've exited for the last time, then you know that you cannot return anymore because just because the number of incoming if you have already used all outgoing, then you already used all incoming, so you cannot go back again, so you can never get stuck. So you are completely free. So once you've fixed the tree of last exit, then the probabilities can be written as a product. Is this claim clear? The number of paths is now just a product of Bernoulli terms, one for every vertex. Okay? Hope it's clear. If not, I think about it at home.
The total sum is random?
What?
The total sum is random?
So, yes, of course. This is just this is like somehow the core of the calculation, but the actual calculation you have to say, for every collection, for every environment, you have to say what are the total number of parts, the total weights. I didn't discuss the probability at all. It depends on the numbers. And then you have you get somehow some kind of you get the density by as a product of one term that comes from the probability that I didn't discuss, and another term coming from the sum number of paths. In short, what we get that the density of the environment, okay, the density of the environment of, which letter do I want to use for that? The density of, say, PE, right? We need for any collections of probabilities on the edges to give you a number, which is the density compared to the, say, Lebesgue measure. We get that it contains all kinds of terms that I didn't discuss, and a sum over spanning trees. Of some product on the edges of the tree of something that depends on the PEs. So I'm not going to write it explicitly because it's not sufficiently important. But what is important here is that you get a term of this type, a term which contains a sum of three, simply from this combinatorial argument that tells you that once you fix the last exit tree, the number of passes has a combinatorial formula. Okay? And this is, of course, can also be written as a determinant using the matrix tree theorem. Okay, so here is the claim. There is an explicit formula for the density. It contains all kinds of unpleasant but normal-looking terms, and unpleasant and not at all normal in this business. The term which is like a long range, which induces long range dependencies because it's basically a sum over spanning trees or a determinant of something that depends on the weights. Questions about this?
Yeah, what is P?
Okay, so this is the probability, say, to get a specific environment. Not a probability, a density, but okay. And P is the environment.
Please come back.
Yes, exactly. Okay. Okay, so more or less 20 minutes have passed, so now I can tell you what's the relation to Anderson. And the point is, the relation is through this formula, that if you look at the green function of the Anderson model, it has a similar formula. In fact, it has two similar formulas. One that you get by supersymmetry, which I will not explain, because even though we had a very nice introduction from Jan, I still think that to explain that in the context of Anderson would require too much time. So let me give you a different way a different, somehow much more elementary way to understand that, which I learned from Eisenman. Random Anderson, of course. So what am I talking? So let's And again, of course, not in one dimension, on any graph. So you take Anderson on any graph. So how does it, what is the operator? So the operator, so you take the operator, okay, the Hamiltonian is, right, it is the Laplacian of the graph plus a diagonal operator, right? This is the graph Laplacian as an operator, or a matrix if you prefer. And this is a diagonal operator, matrix. Okay, and let's subtract also the energy. And the green function is just defined by this formula, right? By an inversion formula, by inverting the Hamiltonian at a given energy. Okay, so let's write one line of that. No, I still need that with me. So let's just call one vertex 0 and write this more explicitly in with respect. Just write one line. I just rewrote it. So then extract V. That's strange because we start with V. We want to get G, but no. Let's do the opposite. Let's extract V out of G. Okay, so that's just a calculation. So what is it? It's delta 0x minus this sum. This, by the way, if somebody is not familiar with notation, this just means y are the neighbors of x. You divide by g of 0x, and you add the energy, whatever. Okay, so this gives you a... But of course, once you have a map between g and v, then the density of g and the density of v are related by the Jacobian, which is just the determinant of the derivative function. And this relation is two-sided. So you get that the density of G is the density of V, which is just a product, times a determinant term, but not the same determinant. Okay, so that's the relation to Anderson. The relation is that the environment of linearly reinforced and the green function of Anderson, they are both random fields with a similar Hamiltonian. With a Hamiltonian that has, in addition to, which in both cases has a big determinant as the term that introduces long-range dependencies. Okay, that's the relation to Anderson. As I said, it's vague, but it's sufficiently close that people consider that as that it should be a model that teaches us something, and in fact the phenomenology is similar, as you will see, to what is conjectured for the Anderson. So if you want, you can think about it as follows. It's a simplified model for Anderson, which gives you two advantages. You can use field methods, which it's difficult to use directly on the Anderson. And you can use probabilistic methods because of this extremely simply to describe interacting random walk. Questions? Okay, I guess everything is clear. Maybe I should have explained the supersymmetric connection. Then it wouldn't be the case that everything would be clear. Okay, so
In what sense are the two determinants similar? The way you describe it, you have two determinants.
I'm saying that the models are similar in the sense that you have that the long-range dependency comes from a determinantal term. They are not the same determinant. In particular, this one's positive and the other one's not. Right here, you take products of positive things. There, if you rewrite the determinant as sum over trees, you don't get positive things. That's the difference. Okay? That's why Anderson is still open, even though linearly reinforced is almost completely closed. Okay? So it's a time model. No, you somehow, if you want, you force the interaction term to have a certain structure that the original doesn't have, and then you utilize that in various ways. But
Do they have the same long-range behavior?
that's only conjectural, because everything that's known is only known. What is proved for linearly enforced is also what is conjectured for Anderson. Okay, so what is proved for linearly enforced? Okay. So first of all, so let's start with the, is it the ordered phase or no? I guess it's the disordered phase. Okay, so what is known? So first of all, let's start with the disordered phase. Okay, let me not, okay, let me, okay, so NED. Okay, now, so far I discussed general graphs, but let's move just to lattices ZD, right? That's the graphs that we are interested most. For NED, A is sufficient if A, the initial weights are the order parameter. That's also, by the way, a surprising fact here. You wouldn't expect such a big dependency, but we will see phase transitions in the initial weights. For A sufficiently small, you have exponential concentration. So, so say gxy decays exponentially in the distance between x and y. And again,
This probability to come from x to y.
the probability to come for x for y, or if you want just, or also, right, it's a probability, yeah, it's the probability to, yeah, if you want, you can define it in various ways, but yeah, the expected number of visits to y when you start from x. So in particular, it's finite, and it decays exponentially. And also, you can define it as the correlation of the environment, right? You have a random environment, which behaves in many ways like your green function, and okay, maybe it's best as just transition probabilities.
D is the dimension, right?
D is the dimension, yeah. Yes, in fact, this is just for any graph, but this particular result is just for any graph. So any graph, you have an A sufficiently small, depending on the graph, certainly, such that if your initial weights are smaller than A0, then you have exponential concentration. The particle doesn't go anywhere. Yeah, it's just random walk, but you know, okay, let me draw a picture, right? Suppose you start with extremely, extremely small weights, okay? 10 to the minus 9. Okay, your first step is still random. But then on the next step, you have something which is essentially 1 compared to 10 to the minus 9. So it will go on this, so it will go back. Make it 2. Go back. Make it 3. Okay, not forever. Because the probabilities to break out are 1 over n, and they sum to infinity. So you will increase this weight a lot and eventually break. And then you will go over all verges which are not 10 to minus 1 for a long time, eventually breaking into a new edge, and so on. So the process does get to every edge. But what happens is that it does that while constructing such heavy weights that most of the time it spends near where it starts, despite the random walk-like behavior. Yeah, no, it's not. There is a reason why people look at this model. It's okay, and who proved that? Okay, so and this is very interesting because it can be proved both using field methods and using a completely probabilistic argument. So using Field's method, it was done by this, Torrey and Spencer in 2010, and then Sabot and Tares, which somehow understood how this was in the context of a supersymmetric sigma model, and then Sabo and Teres understood correctly the connection, how to translate that to a random model. And essentially simultaneously with Omer, Angel, and Nick Crawford. And this is a completely probabilistic proof. You don't need the form of you don't need to look at the determinant for a second. You just need that it has you just pass in a careful way from the reinforced random walk picture to the random walk in random environment picture and back without using any information on what is the environment, and you get the proof. So this is for the, I guess, disordered phase. Okay. Yes. You can.
No,
You
I
can-
not.
Well, the proof gives a value which depends only on the degree of the graph. And not in a terrible way. Some polynomial of the degree. And where is that's the eraser. Okay, what next? Next is okay. Next you would want to see a phase transition, right? Which you would expect if it looks like a field with a with a continuous symmetry. You expect it only in dimension 3. You have, by the way, continuous hyperbolic symmetry in this model. So in dimension bigger or equal than 3, A is sufficiently large. Then first of all, you have transients. So let's just say transients. That's maybe the easiest thing to explain. So transients, the particle simply does not return to its starting point more than a finite number of times, if A is sufficiently large. Yes, this is for, now I'm only talking about lattices. It's true that this result was in fact for any graph, but but let me just focus on lattices because eventually it's a physics-inspired model. So D bigger than 3, you have transients. And this we have only field proofs for that. It's quite a complicated renormalization scheme. You can do a non-renormalization scheme for people interested in graph. If the graph is non-amenable, then you can give a proof that doesn't require renormalization, a more or less direct probabilistic proof, but in lattices you need a renormalization, so the proof is not easy. And this was done essentially by Di Sartori, Spencer, and Zirnbauer. And then if I write Di Sartori every time, I will not have time for anything else. So, and then again, in the more random setup by Di Sartori, Sabo, and Teres. Okay. Questions about the statement? Again, D bigger than or equal to 3, A is sufficiently large, then the walker eventually drifts off to infinity.
But it drifts off like a diffusion?
Yes, diffusively, yes.
see.
It's a diffusive process, yes. I'm not sure, maybe the diffusivity is not in these papers, but in a more, in a later paper of Sabo and Zeng, but it's not, yes. Okay. So what are we left with? Dimension 2. Is there a Kosterlitz transition or isn't there? That's not known. But that's the main, but okay, but let me finish. We'll start with what is known. So, D equal to 2. So the first thing that is known is that is a Mermin-Wagner type result. That for any A, if you look at Gx, it decays polynomially, an upper bound, which might not be precise. It's certainly not precise for A sufficiently small, and it might not be precise for any A. That's what I would conjecture. But at least you have the result. So again, what is the result? We're in 2 dimensions now. We take A, interesting case is A large, so the result is for any A. And we see that the number of, how is that actually defined exactly? So this is, I think, yeah, the expected, the expected number of visits to X decays as you go away from X, but not sufficiently fast for you to be able to simply sum it and say that the process is recurrent. Okay? This we don't know. And this was proved first. I'm sorry for giving so many names, but they're just I'm hiding the fact that there are in fact 2 models. So some of I'm hiding the differences between these results because I consider them as essentially technical. And one result with Ron. And again, these 2 results are done using field methods. Mermin-Wagner is a field technique, right? You take the field, you do a perturbation, you estimate the so, no, I can't move that, right? Okay, I'll just read it out. So there is a result of Merkel and Rolles from 2007, which is for the linearly reinforced, then 2 results for a related model, which is somehow more directly related to to supersymmetry, one by Christophe Sabot, and one of Ron Peled and myself in both in 2021. But interestingly, it doesn't follow that the process is recurrent from that. You would think yes, but in fact, because of the large variability, you shouldn't think about, this is the expectation, but these are, the actual variables have fat tails and are highly irregular. So you can't conclude that the process is recurrent from that. So that's a different result. So let me quote that too, because it required a completely different idea, which is, I think, in my opinion, should be useful also for showing no Kosterlitz towers. But I just erased what I wanted. So Sabot, Christophe Sabot, and Shaolin Zeng, 2021. D equal to 2. Every A, the process is recurrent. So it returns to its starting point infinitely often, which is the original question as posed by the Akonis in 1980. Okay. It's localization, but not as strong as we would like. And the main remaining open question is, in 2 dimensions, is it true that for any A, okay, the large A are the interesting case, you actually have exponential decay? This is not known. This is the main outstanding question.
If this is correct, how C depends on A for large A?
Yes. Yes, good question.
Because I believe it, okay, if we use analogy to understand normalization, it's exponential.
Exponential or super exponential?
Okay, I should.
No, okay,
Yes.
one. Fair enough. Yes.
What is this example?
So again, this is an open question. You are in 2 dimensions. The question is about any initial weights, but the interesting case is big, large initial weights, because for small initial,
Graph.
2-dimensional lattice.
But what is the difference with this?
Here, it's just an upper bound. The question is if this upper bound is sharp.
Ah,
Expectation
the
that
question
no.
is whether you can
Yeah,
improve it to this.
exactly. Exactly. I conjecture, and it seems that Jan is with me, that it should be improvable. The correct answer is actually exponential decay for every A, but it's not known. Questions?
What is the proof?
What?
Why it is not?
Well, Mervin Wagner doesn't give that, right? So,
Techniques are not developed
yes.
on field side.
I think, look, analogous questions are not known for any model, right? You expect it for Heisenberg, for quantum Heisenberg, for, by the way, there are also for, it's an interesting bridge, this model, okay? You expect it also for other non-interacting random walks, and that's also not known. So there is also mutatis mutandis. There are other interacting random walks for which you expect exponential decay for every value of the order parameter, but we have no tools for that because yeah. No, I don't have a good answer why not, but I didn't succeed. And other did, and other too, and quite strong people worked on this family of problems, let me put it this way. But also on this, quite strong people worked on that and didn't succeed.
Let me ask you a trivial question. So, dependence on A is because you add 1. So
Yes.
comparison between 1 and A.
Yes. This is completely, if you multiply 1 by 2, then and A by 2, you get the same problem, yes. Yes, but somehow I formulated it this way because that's the natural parameter in the quantum model, so it's natural to formulate. But yeah, I could have started with initial weights 1 and formulated my parameter as this, what you add.
Another question about G. So, so this G is for the reinforced walk.
Yes.
What is it exactly? G is the reinforced walk.
So it's the ratio between the environments. Yes, I actually said it. I actually probably didn't say it correctly. It's the ratio between the environment. You know that there is an environment.
The law of the environment or the actual? What do you mean, the ratio?
Let's say expected. So you look at the environment for a process started at 0. You compare, for example, the weight of 0 or some edge going out of 0 to the weight of, let's do it for edges. One edge near 0, one edge near x. You take expectation and you take the ratio, and you take expectation. That's the
Ratio of expectation.
okay. The guy near 0 would have weight 1 in all cases, so like of the order of 1. So when you start from 0, the weight of an edge near x. That's the correct definition, because in fact it goes there many times because it's recurrent. So yeah, I was not careful when I said the correct. The whole point how I arranged this talk in order to show you that there is the environment in order to define G. So I'm not using it. Okay, yeah, G is defined via the environment. It's the ratio. It's the weight of an edge near x. That's the correct. Even though the statements about recurrence and transience are the only ones which are really for the random walk. But when I talk about G, I mean then the law of the environment. Okay? Okay, so
Why did you say that weight zero is one? It's actually increasing. What you mean is
no, no, it's increasing, but in expectation it's
increasing. You recur.
no, but the environment is there is a natural. It's not the environment is normalized essentially to be right. The environment is the scale invariant. So think about it as normalized to be one in a neighborhood of 0. Right, an environment. It's an environment for a random walk. So multiplying everything by a constant doesn't change the behavior of the process.
Yeah, so you normalize the total probability.
Yes, you normalize it in a complicated way that comes from the supersymmetric representation, but the effect is like normalizing to be weight 1 at your start.
And you don't literally take the expectation, you have to take a fractional moment.
Yes, you need a fractional moment, yes. Yes. Or you can think about whether the environment is almost, yes, sure, yes, it's the environment, the almost true behavior, or the fractional moments. Yes, you are right, but yes. The expected of the, like in the Anderson, the expected of the environment is infinite because of word identities.
Model,
What?
just modulus of this.
Yes, yes, yes. Okay, so I guess I won't be telling you too much about the proof, so maybe I'll stop here. I used my time, I guess.
Thank you very much. Very nice talk. We had already several questions, but maybe there are some other questions.
Yes.
So, is there anything from here that can be used for the Anderson? Or is this a kind of book for you or something?
Well, I'm sure I tried, didn't succeed. I'm sure others did too.
There's no work like that, right?
No, no.
In some sense, Bauer and Spencer, they feel theoretical, like toy models of which are related with this nonlinear sigma model that I discussed, as far as I know. So it's just one sector of the model, the hyperbolic sector.
Yes, exactly. I didn't say that because I didn't know how many people in the audience I would understand if I said it. But if you take their model, then you get exactly the same green function as for a cousin of linearly reinforced random walk, which is called vertex reinforced jump process. So there is I didn't discuss it, but there is a model in continuous time, which is just identical to the Zirenbauer-Spencer model. So, but to go to Anderson, none of this works because of the positivity problem.
I may just comment that, you see, when I mentioned that the nonlinear sigma model has two variables, at least in this minimal version, has two variables. One is like cosine, and second like cosh. So one is compound, one, and second is. So more or less, Zirenbauer-Spencer model only considers this cosh type, which contains important information, but not full information about Anderson model. And they managed to say something important, but it's not enough because it's decorated by this compact variable, and it makes life much harder. So it's very useful for insight into how it could be, but how it is, we don't know. Not speaking of the fact that still a nonlinear sigma model is very useful, but caricature of a real Anderson, microscopic Hamilton. It's just some limited version, if you like.
Let me answer in a different way. I don't think the field methods are useful because you start from Anderson, you get a non-negative, non-positive field. But maybe the probabilistic methods are useful. Maybe you can bypass the field method and construct some kind of reinforcing random walk that would have the same behavior as Anderson. I didn't succeed, but that doesn't say that can be done. Yes, Sasha.
In the approach, in the Eisenman approach, which you mentioned, this was made to work in one dimension and for some kind of models in almost strict. So what is? It's not. It's a technical. Why can't you get some kind of decay into dimension?
I didn't succeed. That's the only thing I can say about that.
No more questions or comments? Well, in that case, let's thank Gady again. I will have a coffee break.